Hey guys, in this lecture, we'll see what do you mean by aliasing and how we can link that aliasing to the sampling in time domain. So we shall assume that we have a continuous time signal x of t, something like this, where its x-axis is time, its independent variable is time, and y-axis is x of t, which is a function of time t. We'll assume that it's an arbitrary signal, arbitrary continuous time signal. So what we do is we are going to pass this continuous time signal to a switch with sampling interval capital T second. For example, if capital T is 1 millisecond, so this switch is getting open and close for every 1 millisecond. Now output from this switch is discrete in time samples. This is how it looks like. So after sampling, the independent variable changed from small letter t, which was time, to n into capital T, where this small letter n is an integer. It takes only integer value starting from 0, and capital T is the sampling interval. So this is directly related to the switch capital T. And also this small letter n will address the individual samples. The job of this small letter n is to address the individual samples. For example, when I put n equal to 0 here, so 0 times 1 millisecond, say we'll assume that capital T is 1 millisecond. So 0 times 1 millisecond is 0, so it is addressing the 0th sample. If small letter n is 1, 1 times 1 millisecond is 1 millisecond, so it is addressing the second sample. When n is 2, 2 times 1 millisecond is 2 milliseconds, so this is addressing this third sample, and so on. So mathematically, when we are converting a continuous time signal to discrete time signal, it is just we have to replace the small letter t in the equation with small letter n into capital T. I repeat again, in order to mathematically to convert a continuous time signal to discrete time signal, you just have to replace small letter t with this term n into capital T. So we'll see what happens in the next slide. So as I explained in the first slide, so capital T here is sampling interval, and inverse of capital T is the sampling frequency. We denote it as Fs. Say before sampling, the signal is sine omega t. We'll assume that this signal x of t is sine omega t before sampling. This is capital omega. The ohm symbol is capital omega. So where omega is radians per second and f is number of cycles per second. So this is before sampling. So when I sample it, when I say sample, it's nothing but what? I have to replace small letter t by n into capital T, right? So when I'm done with that, so after sampling, I have replaced t by n into capital T. Usually we ignore this capital T and we write it as x of n, which is equal to sine of capital omega into n into capital T. So this n into capital T is small letter t, right? I just replaced it. Why? Because it is after sampling. So what I'll assume that this capital omega into capital T, I'll assume it as small letter omega. So I'll write this equation in terms of small letter omega. So I can write this sine omega n into t as sine omega n. So where the small letter omega is 2 pi f, where omega after sampling is radians per sample, and f after sampling it is cycles per sample, whereas before sampling it was radians per second and cycles per second. After sampling it is radians per sample and cycles per sample. What is Nyquist sampling theorem? So Nyquist sampling theorem says that a signal can be recovered from its samples completely. So a signal can be recovered from its samples completely, in the sense I can from these samples I can recover this signal completely. When I can recover it, only if sampling is done on the condition that the sampling frequency is equal to or greater than twice the maximum frequency of the analog signal, so which is subjected to the sampling. So in short we can call it as Fs is greater than f. In order to recover the original signal completely, Fs, which is sampling frequency, should be greater than or equal to twice the maximum frequency component of the signal. So where Fs here is sampling frequency and Fmax is the maximum frequency of the signal to be sampled. We'll take up an example. If the signal x of t has two signals with frequency f1 has 100 Hz and f2 has 4 kHz. So I have a signal, continuous time signal x of t, where this signal has two frequency component, 100 Hz and 4 kHz. In order to recover this signal completely, what is the minimum sampling frequency I have to take? So as per the sampling frequency, it should be greater than or equal to twice the maximum frequency component. So maximum frequency component here is 4 kHz. So 2 times of that is, so it has to be 8 kilohertz, right? So I have to sample this signal with minimum of 8 kilohertz so that I can recover the original signal, uh, continuous time signal back. Now, what is aliasing? So aliasing, this is actually an informal definition. So it is nothing but high frequency component of the signal will pose as if it is a low frequency component. So I repeat again, high frequency component of the signal poses as if it is a low frequency component. Let me convince you this statement with an example. So consider the following two signals, two analog signals. We have x of t is cos 2 pi 10t, and this signal is added with cos 2 pi 50t, right? So this x of t has two frequency component, one is 10 hertz, the other one is 50 hertz, right? But the thing is, in order to sample the signal, what is the sampling frequency I have to choose? As per the sampling frequency, it has to be greater than or equal to twice the maximum frequency component, right? What is the maximum frequency component here? It is 50 hertz. So I'm supposed to take minimum of 100 samples in order to recover the original signal back. But what I'll do here is I'll intentionally undersample it 40 hertz just to convince you what is this aliasing. Okay, what is the corresponding discrete time signal mathematically looks like? So I have to replace t by n into capital T, right? In order to convert this analog signal to discrete time signal, I have to replace this t by n into capital T, where capital T is 1 by fs, right? And what is fs? 40 hertz. So wherever t is there, I have to replace it by n divided by 40. When I did that, so x of nt is equal to cos 2 pi. So 2 times 10 is 20, 20 by 40. So I end up with 1 by 2. So cos pi by 2 times n. So here it is 50 into 2 is 100, 100 by 40 it is 5 by 2 pi into n, right? Now if I simplify this, I will write this term as it is, whereas this term, instead of writing 5 by 2 is 2.5, right? So instead of writing 2.5 pi, what I'll do is I'll write 2 pi plus 0.5 pi times n. So these two are same, right? So I splitted 2 pi and 0.5 pi. So what is cos theta plus 2 pi? It is cos theta, right? So I can write this term as cos theta, where theta here is pi by 2, right? Pi by 2n. So this I retained as it is, whereas this cos signal turned into cos pi by 2 into n, right? So this corresponds to what frequency? This corresponds to 10 hertz, right? And this signal corresponds to what frequency? This corresponds to 50 hertz. So before sampling it was 10 hertz and 50 hertz. Before sampling it was 10 hertz and 50 hertz. So after sampling I ended up with so 10 hertz and 10 hertz. So where this 50 hertz signal go? So this is posing, this 50 hertz signal is posing as 10 hertz, in the sense this high frequency component which is 50 hertz is posing as low frequency component which is 10 hertz. So this concept is called as aliasing. So bottom line here is, in order to reconstruct the original signal back, the minimum sampling frequency you have to take is 2 times the maximum frequency. 2 times the maximum frequency. If you violate the sampling theorem, if you are not taking enough sample, what happens is that few high frequency component will pose as if it is a low frequency component. So that concept is called as aliasing.